Oh boy.
When I wake up each day, I feel so weary. Try to face the world, but it's so dreary. But I found that special thing that makes me cheery. Time to do music theory. Music theory.
You're watching Adventures in Music Theory with your host, Dr. Robbins.
Okay, so this is part 2 of the presentation on serial atonality. This is just such a big lecture that it takes 2 videos. And let's talk a little bit more about serialism and 12-tone. And one question you may have is, why is it 12-tone? Why do we start with that when we talk about serialism? What's the attraction of the 12 tones? It's this. The composers who start writing this are coming from that place of non-serial atonality that we just studied in the last chapter, or free atonality, and they're basically trying to not establish any pitch as the tonic, any pitch as being more prevalent or important than the others. And what they begin to notice is one easy way to do that is if you hear all the pitches about the same amount of time, then no single pitch is really able to assert itself as the tonic. So that, of course, works best when all 12 chromatic pitches are there, and when they create a collection of all 12 chromatic pitches that refer to, that we create a collection of all 12 chromatic pitches, which we refer to as an aggregate. And an aggregate is just defined as a collection of all 12 chromatic pitches. Whenever a composer is writing a work and he or she manages to have all 12 pitches in a short span of time, we call that collection of 12 pitches an aggregate. And that aggregate collection is a good way to keep it from any single pitch sounding like a tonic. And I think you know which composer is the one who is most famous for having established that idea. But was he the first? Let's wait and see. This may not be the person you're expecting to see, and the name you're not expecting to hear, because I don't know if you've ever discussed Joseph Matthias Hauer before, but he was a German composer and theorist in the early 20th century who came up with a system of what he deemed tropes. And those tropes were basically a way Hauer had where he would take all 12 pitches and he would divide them into 2 groups of 6 pitches, which we would call hexachords. But instead of calling them hexachords, Hauer called them tropes. Hauer's idea was this. He noticed as long as all 12 pitches were roughly equally represented, there was no good sense of any single pitch being the tonic. So he was creating the atonality he wanted. But he didn't insist that all 12 pitches be played in a particular order like we find in serialism. He just grouped it into 2 tropes of 6 pitches each and said you need to play all 6 pitches in the first trope in sort of any order, and then you need to go through all the 6 pitches in the second trope in any order, and that will create this sense of aggregate collections without any pitch being a tonic. So, if you'll look, you'll notice that on the collection I've got there, the first hexachord has F, A, G sharp, B, D sharp, E. And if you look at the little melody at the bottom, you'll notice the first pitches all come from that first trope, but they don't necessarily happen in the order they're written in the trope up top. They just happen. But those 6 pitches happen, and then the next 6 pitches come from the second trope. And that's how those measures are organized. So it's not quite as rigid a system as we find in serialism, but it does create aggregates. And Hauer thought of it in 1919. But the person who we think of most prominently when we think about the originator of serial atonality is, of course, Arnold Schoenberg, who in 1923 writes what we think of as the first actual 12-tone piece, and who puts forth what he refers to as his system of composing with 12 tones. And Schoenberg's the person who gives us the ideas we think of as characterizing classic serialism. The idea that the pitches happen in a specified order or series, a prime form, and then that order or series can be inverted, retrograde, and retrograde inverted. So Schoenberg's idea ultimately proves more compelling than Hauer's. And there are plenty of composers who pick up Schoenberg's ideas and continue composing in that form for decades. In fact, we can probably still find people out there who are doing it today. And here we have a passage of music from what is ostensibly the first 12-tone composition, Schoenberg's 5 Pieces for Piano from 1923. And this is the 5th movement, the waltz movement. And if you look at it, you can see how Schoenberg utilizes his 12-tone approach to composing. Looking at the melodic line in the right hand of the piano at the beginning, you'll notice all 12 pitches occur, and no pitch recurs in that melodic line until each other pitch has happened. And I've gone through and I've labeled them with fixed 0 integers. And this is a very, very straightforward approach to 12-tone composition. In fact, it's usually not this rigid, but this is certainly a good first example of how 12-tone composition works, because we have the tone row happening melodically right at the beginning. And of course, since the melody has no pitch repetitions in it before all 12 pitches have been exhausted, that melodic line in the treble clef is a good example of a pitch aggregate, to use our new word of the day. In fact, let's say it again, aggregate. And here's what it looks like if we take that tone row that's presented in the right hand of the piano and those opening measures of the Schoenberg piece, and we turn it into the top row of a matrix. And this is a pitch class matrix, meaning we're using letter names to show the identity of the members of the matrix. So all we do is we write down the letter names of the notes in Schoenberg's melody. And it starts out C sharp A B, so I write C sharp A B in those first boxes. And this is a very straightforward 12-tone composition where you can just look in the melodic line in the piano and decide, well, that could be the tone row right there because it has all 12 pitch classes represented. Not all 12-tone pieces are as easy. You can't always be guaranteed that you can go in and extract the row from some melodic line. Sometimes there's more unscrambling that we have to do, and the row might be shared between the melody and the accompaniment or whatever. But for this piece, we could perhaps assume that opening melodic line in the right hand of the piano is a row. And if we were analyzing, we might decide, since that's the first thing we notice melodically, we're going to put it at the top of our matrix and build our matrix off of that. Or instead, I could choose to build my matrix as an integer matrix and identify all the members by number instead of by letter name. And you can look and you can see that what I've done in this particular integer matrix is I've decided to make it a fixed 0 integer matrix, working from the assumption that C is always going to be 0, and C sharp will always be 1, and D will always be 2, etc. And since Schoenberg, when he actually writes the notes of his piece, starts his melody on C sharp, I'm going to write 1, which is the integer identity of C sharp, and fix 0 for my first box there. And once we have our prime form of the row put in, the next thing you want to do when you're building a matrix is write your inversion row down that left side column. And we're going to just flip our intervals upside down. And if we're working with numbers, then there are a few different ways to do that. But since we're doing the prime row, when we go from 1 to 9, we're going up 8 half steps. So the next thing we need to do then is, when we're starting down on the inversion row, we need to think, so what's down 8 half steps from 1? And there are a few different ways to think about it. The clock thinking might be as good as anything. You could think about, well, if I was at 1 o'clock, what time would it be if I went backwards 8 hours? And you can visualize it would be 5 o'clock. The other way you could do it is this. Whenever we invert an interval, the interval and its inversion have a total of 12 half steps between them. So if I go from 1 up to 9, that's 8 half steps. So if I want to know what the inversion is going to be, that's going to have 4 half steps. So I go from 1 up to 5, which is going up 4 half steps. And then the next one's a little bit easier. You know, the original row goes from 9 to 11, up 2 half steps. So I just need to figure out what's down 2 half steps from 5. That's back 2 to 3. But anyway, however you do it, you want to get that column that's your inversion row down there next. So actually we've got 2 row forms completed now, and we can get 4 identities from it. Because if I read from right to left, or excuse me, from left to right, I would have the row form we would call P1. And if I read from top to bottom, I would have the row form we call I1. If I read from right to left, I would have the row form we call R1. Because remember, we're going to name the retrograde row for the pitch it ends on. And if I read from bottom to top on that column, I would have RI1. Because we also label retrograde inversion rows for the pitch they end on. And let's look at what this thing would look like if we were building it as a pitch class matrix instead of an integer matrix. So as a pitch class matrix, some people might find it a little bit easier to do the inversions because you can think in things that are more like the more familiar diatonic style intervals. Like when we're looking at the prime row, we go from C sharp to A. That's down a major third, if you want to think in terms of old school labels. So when I'm doing the inversion row, I want to think about, well, what's up a major third from C sharp? And literally, a major third up from C sharp is E sharp, but for the sake of atonal music, it's always easier to say F natural rather than E sharp. And when I go from the second to third note in the prime row and go up a whole step from A to B, then I just want to think down a whole step from F, and I could go to E flat, or I could of course call it D sharp. It wouldn't really matter for this style of post-tonal music. But at any rate, however you do it, you can then complete your matrix, because there are those tricks we learned in the earlier lesson about you can just write down transposed versions of the prime row starting on whatever pitch is in the inversion's first column there, or there are other things we can do. But when you have a complete integer matrix, it's going to look like this. All the squares are filled in, and if I wanted to check this and make sure it was correct, I could look down every single row or every single column, make sure I had each character from 0 through 11 represented once and only once. Or, of course, the quickie shortcut we can do that's easier is look in the upper left-hand corner, follow that diagonal down to the lower right-hand corner, and see if it's the same member each time. And it is. You'll notice there's like a diagonal line of ones, or C sharps, that runs diagonally from the upper left to the lower right of our matrix. And that's one of those easy ways to check your work and make sure you're constructing your matrix the right way. It should have that diagonal in it. So there we've got a nice fixed 0 integer matrix set up. The only thing that's not done is I haven't gone through yet and labeled all the row forms. But I've got to start there with the first 2 P forms and the first 2 I forms and the first 2 retrograde and retrograde inversion forms labeled. So you can figure out how to finish it from there. Okay, and let me show you what might be another way to do that inversion row. That's sort of the trickiest part of setting up a matrix for people, is getting that inversion row. So this is a way to do it using numbers that actually is sort of easy. What you want to do is you want to look at the number that's in your upper left-hand corner. And we're looking at it because we're trying to get an index number, because we're going to use index number inversion to get our inversion row. So look at that number in the upper left-hand corner. It's a 1. I've got it circled. Double it. And when you double 1, you get 2. You all knew that. We're doubling it because 2 is going to be our index number. And since we've got 12 half steps and stuff to deal with, and 2 is such a small number, we need to realize that the index number could be 2, or it could also be 12 plus 2, which is 14. But the index number we're working with is 2 or 14. So if you want to know how to use those index numbers to make the row, or the inversion row, that column that goes down there, what you do is this. Look at the diagonal counterparts and make sure they always sum to the index number, to 2 or 14. So we add that first number in the upper left-hand corner on itself, right? 1 plus 1 is 2. That sums to our index number. And then we go from there. So we're going to combine things diagonally. Like if you look at what comes second in the prime row, it's 9. So the thing that goes second in the inversion row is going to be whatever we have to add to 9 to get to our index number, which is 2 or 14. So we do a little in your head algebra here. What plus 9 equals 14? 5. So we put a 5 in that column, or in that box in the inversion column. Then we move over to the next number in our prime column, which is 11. Do the same algebra. What plus 11 equals 14? I like 3. What plus 7 equals 14? How about another 7? And then going across the top row again, what plus 8 equals 14? 6. So we put that in the inversion column. And then back in the upper column, what plus 6 equals 14? That'd be 8. 10 plus 4 equals 18. So we put that in the inversion column. And 2 plus 12, or remember the index number can also be 2, so 2 plus 0 equals 2, which is our index number. And 4 plus 10 is 14, as is 3 plus 11. 0 plus 2 is 2, and 5 plus 9 is 14. And if you want to check and make sure that your index number is right, if you don't trust your ability to add to 14, the other thing you can do is just look in that vertical column, make sure you see every character from 0 through 11 falling there once and only once. And if you did it that way, congratulations, you got it right, and you just learned how to build your inversion row using index numbers. It's a good trick to know. Okay, so let's look at the actual notes of the piece and the matrix together. And when we do that, we're going to get something that comes out a little bit different here, because the way we tried to analyze this initially, which wasn't bad, is we just looked at the treble clef part and realized, oh, well, that's a row form. That's all 12 pitches. We could call that P1. No reason to not do that. But when you go to look at the left-hand part, it's trickier. It's trickier in part because the left-hand part has chords in it. And chords are sort of, by definition, not very amenable to 12-tone analysis, which we call serial analysis. And of course, serial means notes in a series, one note after another. And something like that very first thing in the left hand, where you have G flat and B flat and D, all three happening at once in a chord, it's hard to know, so which one of those notes is first in the series? It's not necessarily going to be that it's the highest note or the lowest note. It's just a chord. And chords make analyzing this tricky. And if you go look at the matrix, what you'll realize is it's G flat and B flat and D, which is 6 and 10 and 2. And I don't see any row that starts with 6 and 10 and 2. I don't see a prime form that starts that way with any of those three notes, all three being the first three notes. I don't see any inversion rows where those are the first three notes. I don't even see any retrograde or retrograde inversion rows where those are the first three notes. But what's happening is this, and the reason I'm using red fonts is to sort of point this out. the red fonts and the red boxes are showing us that what Schoenberg is doing is creating aggregates. And if you look at that red box, all the notes in that red box are an aggregate collection of the pitches in P1. Because the melody in the right hand, in the treble clef, that's the first 5 pitches of P1. And if you look at what's going on in the left hand, that's the last 7 pitches of P1. And let me put some little arrows in the matrix to show you that. That arrow that just showed up, that starts halfway through the P1 row, that's showing you what's in the bass clef in that red box. And this next arrow is showing you what's in the treble clef in that box. And then if you look in the blue box, you realize that that forms an aggregate collection as well, because after the left hand finishes doing those last 7 notes, it goes back and does the first 5 notes. And that little blue arrow is showing you the D flats actually at the end of the red box notes. And then what's going on in the right hand in the treble clef is that's the right hand completing the P1 row by doing the last 7 notes. So that's sort of the craft and art of writing this 12-tone music, is you don't just go through and do rows higgledy-piggledy as melodic things, but composers try to find ways to be a little more crafty and subtle with it. And here we have something going on to show us that there are a couple different ways to look at this. The bracket across the top there with P1 written on it is showing us that we can envision the treble clef part as being the P1 row according to this matrix we've constructed. And if we look at the left hand part, then we can construe what's going on in the left hand as being an aggregate collection, which basically is what happens if we start in the middle of the P1 row on 6, and then once we get to the end we go back and make up the 5 notes that we missed to get an aggregate collection. And the last slide, of course, was showing us how you can also think about the first 2 measures, treble clef and bass clef, form a pitch aggregate, and the last 2 measures, treble clef and bass clef, also form an aggregate collection. And if we were to go through this whole piece, and we're not on this video at least, then we'd probably find other opportunities to see aggregate collections being formed by the 2 hands of the piano part. Like this thing from the next system on down, where you can see that if you look at just the melodic line, it appears to be starting at that midpoint again on the F sharp, B flat, D. That's the 6-10-2 in the middle of the P1 form. But if you look at the numbers I've written across the top, you'll realize that those numbers take into account all of the treble clef and bass clef pitches, and they don't repeat any pitches until the very end of the line. Then you can see the 6-10-2 comes back, but it doesn't come back till all the other pitches have had a turn first, so we get an aggregate collection. But that aggregate comes about not just by sticking the row form in the left hand like a melody and being done with it, but by taking it and finding ways to rather cleverly and musically share it between the 2 hands. And it passes from the left hand to the right hand and back. And there are even places in it, like in the second measure from the end, where you can see how Schoenberg writes harmonic intervals, where he's got that E and that A on top of one another. And that's something that we need to hear. Excuse me, that's a C and an F. But that's something that we need to hear as the last 2 pitches of the row. So that's sort of the, as I said, that's the craft of doing this, is figuring out ways to not just go up and down and sideways through your row, but to actually find ways to make it musical. And some of that happens when you share different row forms between the parts.